Hello and welcome to this section EKS networking. Now the purpose of this course is to focus on the networking, and when it comes to the EKS it is all about the Kubernetes networking. Now I understand that not many of you or not all of you might have good understanding of containers or microservices or Kubernetes, and that's where I thought I'll just briefly cover what are containers, why we need this, what are microservices, why we need this, and then why we need Kubernetes. But if you're already aware of all these topics, then feel free to directly jump to the topic of EKS networking. So let's start. So why we need containers? So let's go back in time. Earlier we used to run our application directly on the physical hardware. So there is a hardware which contains the CPU, memory and the disk, and then we put an operating system and we run the applications. So it used to work well, but there are many problems with this physical hardware thing, and one of the important problem is resource allocation issue. What if one of the apps grabs all your CPU or a memory? Then other applications might starve for the hardware resources. And then how do you solve this problem? Earlier days, you could run multiple hardware boxes, and on top of those, you run multiple applications. So this gives you better isolations of the applications, but then it also introduces some problems. Problems like you are not able to fully utilize the hardware, right? You might have unused capacity in this hardware. Operating system overhead is there because now you're putting operating system in every hardware box. Then application portability. Application portability means can you run the same application on any other hardware? Now in older days, I remember that you have to install the operating system, you have to install all the libraries and packages, and then you have to run your application on top of it. Now this is a long process. Maybe sometimes it used to take weeks to run application on another hardware because all these things needs to be done manually. Deployment automation wasn't really possible. At the max, you could write probably some shell scripts and then you spin up the Linux machine and then you run those shell scripts. But then due to a lot of customization and dependency on the manual configuration, those shell scripts would fail more often or not. So you could achieve it, deployment automation, but not to the best. Scalability. What if there is one instance of application and you want to run more? That means you need to first grab the hardware, then repeat this process of putting the operating systems and then running that application. So it takes a long time. It's not really a scalable thing. Security and isolation, it is better because there is different physical box. That means no two applications running on different boxes can talk to each other. So it's really secure in that sense. Finally, you could have choices of operating system on different physical boxes, and then you get that flexibility to choose underlying operating system. But then you see a lot of gray boxes there, and that's the problem that we want to solve. So over the time, we move to the virtual machines. Virtual machine is nothing but hardware virtualization. Rather than directly running an application on top of the operating system, you would run virtual machine, and for that you need a hypervisor in between. Hypervisor isolates or abstracts the physical hardware for the machines. So every machine which runs here feels like they're running on actual hardware, but they are running on the hypervisor. Now there are two types of the hypervisor, type 1 and type 2. Type 1 run directly on the bare metal, and most of the cloud providers use type 1 hypervisor, for example KVM or Zen hypervisor. But there is type 2 hypervisor. If you have ever launched Oracle VirtualBox, that's a type 2 hypervisor because it runs on top of the operating system. Now here in this picture, I have shown here the operating system. That means it's a type 2 hypervisor, but doesn't really matter. Ultimately, you get a virtual machine which has its own operating system. You put your binary and libraries on top of it, and then you run your application. Now these virtual machines are completely isolated. They feel like they're running directly on the hardware that they own, but that's not reality, as you understand. Now, if you see this virtual machine architecture, of course, it solves some of the problems that physical hardware cannot solve. So let's look at those. Hardware utilization is better because the hardware capacity is now distributed among these virtual machines. So if one machine needs maybe 2 GB of RAM, another machine needs 4 GB of RAM, you can do that allocation, and hypervisor will make sure that virtual machine cannot use more than the allocated hardware resources. Operating system overhead is still there because every virtual machine has its own operating system, and you know that operating system itself takes some CPU and RAM to run. So there is an overhead there. Application portability is quite better because you know that you can take an image of the virtual machine and then you can run that image onto the another physical hardware on top of the hypervisor, right? So this image size is typically 1 GB I have seen, but it is portable. You take this image, copy it and run the virtual machine. You don't need to install these binaries and libraries and application into that machine because it's already there. So it's better application portability, but not the best probably. Deployment automation is possible. Now, if you have ever spun the EC2 instance, you are doing an automation, right? You are making an API call and it spins up the EC2, which is nothing but a VM in the cloud, right? And in that sense, you get a deployment automation. Scalability is possible. Like in AWS, you can launch many VMs over an API call. So you can scale that as you want. And security and isolation, of course, it is there because hypervisor is managing that. So these apps do not communicate unless you provision a network connectivity between these two apps, right? And then you get an operating system flexibility because different VMs could have different operating system. For example, first VM could run maybe Linux, another VM could run Ubuntu or CentOS. So that's very much possible, or even the Windows, right? So you get that flexibility. So VMs are better, of course, you can see here, but there are still some challenges with respect to the operating system overhead and then application portability, automation, and scalability. So as you might have guessed, the solution to this is nothing but the containers. So what are containers? Now containers are a little different to the VMs. In case of VM, your hardware is shared, but in containers, your operating system is shared. Like hypervisor does the hardware virtualization, containers uses the operating system virtualization. Now in that sense, you put in container runtime engine on top of the operating system and you just package your application and required binaries and libraries into the container image and you run it on top of your container runtime engine. That's it. There is no operating system. All these containers think that they are running on a dedicated operating system for them, but in reality, there is a shared operating system. Now this greatly reduces the overhead of running the operating system, and that's where these container images are very, very light, maybe in few MBs. And if you compare that to your virtual machine images, they are probably in hundreds of megabytes or maybe sometimes in gigabytes as well. So containers are the lightweight images and you can run it anywhere. As long as you have the container runtime running somewhere else, you just package the container image and run it there. So the benefit is better hardware utilization because ultimately it's same hardware and you can run as many containers as long as there are hardware utilized. Now in case of containers, it makes sure that containers cannot use more than the allocated resources, very much similar to the virtual machine, but now you have control at the container level. Further, there is no operating system overhead because you are sharing the operating system. So container image doesn't contain the full operating system there. Application portability, as I said, container images are very light. You can just make an image and run it anywhere. Something like this. If you are another host and you have container runtime, you just make an image and port it. Deployment automation, now that would depend on which kind of tools you will use. There are many tools in the market. Now, if you heard about Docker container, there are deployment tools like Docker Swarm, Docker Compose, which can be used, but there are many advanced tools as well, which you can use for deployment automation. Scalability, with one call, maybe you can increase the container from 1 container to 10 containers, very much possible as long as you have underlying hardware resources available. With respect to the security isolation, there are some concerns because all containers are running on the same container runtime engine, which shares the operating system, but with the right tools, you can have a required isolation in there. Finally, with respect to the operating system dependency and flexibility, as long as the container runtime engine supports the underlying host operating system, you can run your containers anywhere. So container doesn't have hard dependencies on the operating system as long as container runtime supports it. So you get all that flexibility. So that's what the containers are, and then they provide you all these benefits which we have captured here. Now another term that you might have heard recently is microservices. So let's now look at what are microservices and then microservices and containers together, how they can solve some of these problems. Okay, so imagine you have the virtual machine and you are running one application inside that. Now, if you closely look at this app, maybe it's one e-commerce kind of application, and then this e-commerce application further has the individual components. For example, there is a front end in the form of service A, there is a backend service, there is a payment service, billing service, maybe notification to the customers about their purchase. So you have designed this application by applying the microservices architecture or design pattern. That means every service performs their own operation, but still it's one single application. And then you are implementing in a form of maybe classes in terms of Java, or different functions in terms of C or C++ language likewise. So one app consists of multiple services, but then overall app, you see, it's a monolithic application, right? It still is deployed as one single application. Now, what are the challenges if you are putting all services together as a monolith application? So let's see that. Now, typically with monolithic application, one of the problem is all the applications or services needs to use the same underlying language, because you are using the same libraries, right, underlying. That means all these services needs to be maybe a Java based, or for example, they all needs to be .NET based. So you don't get a flexibility where one service is written in Java, another service is written in .NET or Python. So there is a lack of flexibility with choice of the development language and the framework. Now all services use common underlying libraries, as I said, and due to that, changes in one service may break another service, of course, because say one service depend on some of the version 1 of the library, and you change that to version 2 for one of the service, but then other service are using the same library, and that's where those services can be broken. Third problem, change in a single service needs a deployment of an entire application, because this is one complete app. So if you need some changes to be going into your application, you need to package the full application and then you need to deploy it again, right? Which is not very efficient, because you just changed one service and you are redeploying the whole app. Finally, if you want to scale, for example, you are having front-end service and the back-end service, and then you are exposing a lot of APIs, and your back-end service needs to be scaled. Maybe not many people are using your web UI, which is front-end, but then you have exposed the backend APIs to multiple third-party systems, and then now they are invoking your API. Now you need to only scale the backend. But in case of monolithic application, it is not possible, because everything is combined as one application. So how would you scale? You will create multiple instances of complete app rather than a one service in particular, right? So that's a challenge, not possible to scale individual service, and need to create another instance of a whole application. And then you deploy that on a separate virtual machines or maybe physical host, and then you need to load balance the traffic too. So microservices solves that problem. Now we already talked about microservices in the sense that you design the application, but in real sense, if you say microservices, they should be running independently of other services. That's real definition of the microservices. So now here we are just removing that boundary of monolithic application. Now all these services can stand on their own. And now you can see here the benefits are we get to develop these microservices in their own languages. Maybe for front end, Java is better. Maybe for backend, Python or Go is better. So developer can decide which platform or language they want to use to develop their microservices, right? And then you can have multiple instances of one service. That means you can scale these services individually. So you get flexibility of the language and the framework. All services do not use common underlying libraries, which means if you are making changes to one service, that does not break the other services. Further, if you want to redeploy the new version of one service, you don't need to redeploy entire application. Only single service can be deployed. And then it's possible to scale individual service. As you can see here, I have 2 services for Python, and then I can load balance only that instead of deploying entire application and load balance across the application. So these are the benefits of microservices, but then question comes, where should we run these microservices? Shall we run it on the physical box or a virtual machine or the containers? And I'm sure you might have guessed that the best place to run this kind of microservices is the containers, but then it's not always. Sometimes if your microservices are simpler, There are not many services, even you can run those on the VM as well. So it would be depending on how complex your microservices are and what kind of scaling requirement it has. Does it always scale? Does it serve the consistent traffic? Probably you don't need to scale often, then probably container doesn't make sense. Likewise, depending on a lot of parameters, you will decide whether to run on containers or you can also run on the VMs. So here we are talking about containers, and let's see how microservices and containers together can solve some problems. So we are saying that we'll run microservices on the container, and then one service can be run as one container, another service as another container. Likewise, you can go on. The benefits are, of course, you can scale it, you can port it. All those problems that we saw earlier can be solved with microservices and containers together. Now, this is all good. We are now moving to microservices and containers, but always there are some challenges, right? If you're running just few containers, that's okay. But if you go on running hundreds and thousands of containers at scale, then it becomes a problem. So let's look at some of the challenges or what it needs when you want to run these containers at scale. So suppose you have a lot of microservices and a lot of containers, and you have physical host on top of it, you deploy these microservices and containers. So you run first container as a microservice, another one, likewise, right? So you need some kind of tool which places these containers on respective host based on how much hardware resources you have utilized so far. So it will go on deploying this across multiple hosts. I have just shown 2 hosts, but this could be tens or even hundreds hosts, right? So you need some kind of service which manages the deployment of these containers across these hosts. So it will monitor the host physical resources, maybe CPU and a RAM, and it will see this particular host has available CPU and RAM, and it will deploy then additional containers on that machine. So you need some kind of deployment orchestration for your containers across the different physical hosts. So that's one thing that you need. Second, you need a load balancing because now you are running multiple instances of the same microservice. Then of course you need a single entry point for that service. That means a load balancer is required. And if there are hundreds of services, that means there will be hundreds of load balancers. And which essentially need service discovery and the load balancing. And we'll talk about service discovery in later section as well. But service discovery essentially means if service A wants to talk to service B, how would it know where that service is on which host and how to connect to that service? Then what if one of your microservice or a container goes down? You need a tool which can create a replacement instance or replacement container for that. So you need a self-healing kind of ability as well. Finally, you need inter-services communication. Now you see these multiple microservices talking to each other. So there should be some mechanism through which they communicate with each other. So inter-services communication also becomes a challenge. And also you need to monitor this. How much services are doing, how much CPU RAM they are using, are they overloaded? So you need efficient monitoring for these services as well, right? So putting it together, you need some kind of intelligent layer which can manage the deployment orchestration, service discovery and load balancing, self-healing, inter-services communication, monitoring, and much more for you because you are operating at scale. Because if you look at all this together, there is a lot of complexity and you need tool to handle this complexity well. And the answer to this is really Kubernetes. Kubernetes does exactly what is required here. Now, Kubernetes is also represented as K8S as a short form because there are 8 letters between K and S. So Kubernetes is a portable, extensible open source platform for managing containerized workload and services. And this is an official definition of Kubernetes. And this is a link below here. You can visit this page and you can read all about the Kubernetes services, components, and very good documentation is available on there. But essentially it does the same thing. It gives you service discovery and load balancing, automated rollouts and rollbacks, automatic bin packing. That means it understands where I need to deploy these containers. It keeps track of all the hosts, their physical resources availability, and then it automatically deploy those containers on those hosts. Self-healing is possible, secrets and configuration management, storage orchestration, and there are many more features that Kubernetes offers. But ultimately, the crux is Kubernetes allows you to orchestrate the container management at scale. and that's what we'll see in the next lecture. So hope that is clear. And now with that, we will now move to Kubernetes architecture, and then we'll move to the EKS networking. So thanks for watching.